Direct stiffness method for plain trusses. You know what is a truss. So application of direct stiffness method to trusses. Okay. So analysis of plain truss using direct stiffness method. And first of all, you should know what is the element stiffness matrix Ke for a truss element. So in the previous classes, that is for continuous beams, we have derived element stiffness matrix for beam element. Like Ke is equal to 6, that 12A by L square, 6A, that 4 by 4 big matrix were there, right? So that was the element stiffness matrix for a beam element. Now, similar to that, we have to derive element stiffness matrix for a truss element. Okay, in trusses, we have the axial forces only coming. Okay, so for example, if we consider a 1 degree of freedom node, so 1 degree of freedom per node. So if this is one node, you may consider a truss element like this, any member, say this member. So I have taken it horizontal. So this be the first degree of freedom, this be the second degree of freedom. So 1 degree of freedom per node. So I have named it 1 and 2 coordinates. So the Ke matrix will be a 2 by 2 matrix. So from the first principles, or by using the physical approach, you can find the Ke matrix. How will you find? You have to apply D1 is equal to 1. So in direction 1, you have to apply unit displacement. Find the forces in direction 1 and 2. Similarly, you may apply unit displacement in direction 2, then find the forces in direction 1 and 2. So here when you apply unit displacement in direction 1, so let D1 is equal to 1. So what are the forces developed? It will be AE by L. You know, PL by AE is delta. That you have already studied in engineering mechanics. So it is delta or D, whatever it is. From that you can write P as AE into delta by L, or delta is equal to 1 means AE by L will be the P value, or it is a stiffness K. Okay, so the K11 is equal to AE by L. So it is plus AE by L in the direction of application of the displacement itself, or in the direction of coordinate 1 itself, the force occurring. Okay, and here the force will be in the opposite direction, AE by L, and it is opposite to direction 2. So it is minus AE by L, K21. This is the force induced in direction 2 due to unit displacement in direction 1. K21. The unit force induced in direction 2 due to unit displacement in direction 1. Okay. Now, similarly, you can apply D2 is equal to 1. At node 2, you may apply unit displacement D2 is equal to 1 in the direction 2. So you have to find the forces in direction 1 and 2. And you can write K12. The force induced in direction 1 due to 2 is minus AE by L, and K22 is AE by L. And when you arrange it like this, K11, K21, K12 and K22. Like that, when you write it, you can take AE by L outside, and 1 minus 1 minus 1 and 1 is the Ke. It's for a truss element or bar element having 1 degree of freedom per node. If you are considering 1 degree of freedom per node, and usually we will consider 2 degree of freedom at each node, and this is only required for doing the problems. Okay. And for a truss element, so I've considered 2 degree of freedom per each node. That is a displacement along the axis and the perpendicular to axis. So these are the 2 directions: direction 1, 2, then 3 here and 4 here. Okay, so 1, 2, 3. If I am considering a truss element like this, and you have to apply displacement D1 is equal to 1, then D2 is equal to 1, find the forces in all the directions, then D3 is equal to 1, you have to find the forces in all directions, and like that. So whenever you write D1 is equal to 1, that means along the axis I am applying D1 is equal to 1. What are the forces? There will be AE by L in the direction 1 and minus AE by L in direction 3. And there will be no force in direction 2 and 4. Okay, and when I apply D2 is equal to 1, that means I am applying a vertical displacement at this node, like this. Then the force induced, there will be no member in that direction. So there will be no force induced in the member. truss element. So that is K12 is equal to 0, K22 0, K32 0, K42 0. And similarly, you can apply D3 is equal to 1 and D4 is equal to 1 and find the corresponding forces. And whenever I arrange this KE into a matrix form, I'll get AE by L into 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 and 0 0 0. So this matrix you have to by heart. And this is the KE matrix for a truss element having 2 degrees of freedom at each node. That is 1, 2, 3 and 4. So this is 3 and 4, 1 and 2. If you are having a truss element like this, your KE element stiffness matrix is like this. AE by L into 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 and 0 0 0 0. This is the KE matrix. Okay. And now whenever you consider any truss, okay, now I have derived the KE matrix along the axis. Here there are 2 types of axes called global axis as well as local axis. That means whenever you consider this truss, you may consider this truss, plain truss like this. If you consider this element, the x-axis goes along the global x-axis, and this capital X and Y is called the global x-axis in which the structure is oriented. But if you consider the inclined element like this, so its axis is along this small x and small y direction. Okay, so that is not the same as the structure. So each element is oriented in different directions. So we have to make sure that all the KE matrix is written in same axis. Okay, so that is one major problem whenever you consider the trusses. Okay, whenever you consider plain trusses, there are 2 axes. So you have to rotate the axis of each element to a global coordinate system, that is capital X and capital Y system. Okay, that is the structure oriented axis. Clear? So you have to make sure this transformation KE matrix I have derived. This is according to the this is along the axis and perpendicular to the axis for any element. So you have to apply some transformation matrix in order to transform this KE matrix obtained in local coordinates to global coordinates. Okay, so here there are 2 sets of axes. One is the capital X and capital Y, which is called the global axis in which the structure is oriented, and small x and small y, for each element it is different. If you consider this element, this will have a small x and small y, and if you consider this element, it will have a x and y, and if you consider this inclined element, it will have another x and y. Like that, the local axis of each element will be different. So you have to convert it into global coordinate system. Okay, we'll derive the expression for that. So in case of truss analysis, stiffness matrix is first formed in local coordinates and then transformed into global coordinates by the process of rotation of axis. That is called rotation of axis. Okay, and for this purpose, we'll be using the transformation matrix. I'll derive the transformation matrix. This one you may have already known. So I have taken a point P in a plane. So let this capital X and capital Y be the global axis. Now I am going to take another axis, local axis, small x and small y, such that local x-axis makes an angle theta with the global x-axis. Okay. Now the coordinates of P, x and y be the coordinates of P in local axis, and capital X and capital Y be the coordinates of P in global axis. Okay, and if this is the data, you can convert small x, write small x and small y in terms of capital X and capital Y. You have to write small x and small y by using trigonometry. You can take a small x as you may divide this part of cos theta, I mean you may divide it like this, and this value plus this value, and like that you can use trigonometry. I'm not explaining, that will be very difficult to explain in this platform. So you may try to do this. Okay, you may try to do it by yourself. So you may consider 2 axes, capital X and capital Y. You may consider any point P. Let this be the axis, small x and small y. Small x and small y. So the coordinate of this point P in global axis are capital X and capital Y correspondingly. In the local axis, it will be small x and small y. and try to write using trigonometry small x and small y in terms of capital X and Y. So you will get small x is equal to x cos theta plus y sin theta, and y is equal to y cos theta minus x sin theta. I think you have already studied this in mathematics course, okay, or in the first year mechanics or something like that. You have already studied this. Okay, so the coordinate small x and small y of the point P can be written as if you rearrange this equation into a matrix form, you will get cos theta sin theta minus sin theta cos theta of capital X and Y. So this is a vector of local coordinates, and the right one is a vector of global coordinates. And this matrix, so the transformation of local coordinates into global coordinates, that matrix is this is equal to, okay, so x y is equal to this cos theta sin theta minus sin theta cos theta into capital X capital Y. So this matrix is called transformation matrix or rotation matrix, which is denoted by the letter R. Okay, so R is the matrix, rotation matrix or transformation matrix. Okay, so it is that is for a point coordinates alone, so we'll discuss later on. So R is a rotation matrix, and it has a property, the R transpose will be equal to R inverse. So the inverse of this matrix is same as the transpose of a matrix. Okay, now we have written xy is equal to R into xy. Similarly, we can write U is equal to R into D, where U is the element displacement. The element level displacement is denoted as letter small u, which is equal to R into small d. D is the structure displacement. So here the element level coordinates can be written is equal to some rotation matrix multiplied by the structure coordinates. So the structure coordinates multiplied by the rotation matrix, you will get the element level coordinates. Similarly, you can write D multiplied by R, pre-multiplied by R, or R into D will get U. Similarly, R into P, P is a force in the structure, can be written like this. R into P can be, when you multiply, you will get small p, which is called the element force. So element displacement is equal to rotation matrix into structure displacement. Element force is equal to rotation matrix into this P, force in the structure. Okay, we'll use this equation later on. So now we'll move to the stiffness equation. So you all know the stiffness equation for the element can be written as Ke into U is equal to P. Ke, the element stiffness matrix multiplied by the element displacement, will give the element forces. Okay, Ke into U is equal to P. Okay, and you can write Ke into U, you can write as R into D. So Ke into R into D can be written as is equal to R into P. So small p can be written as capital R into P, like this, capital P. So capital R into capital P you can write, and pre-multiplying with R inverse, you'll get R inverse Ke into R into D as R inverse R into P, and you know R inverse R is I. Okay, so Kg, this term R inverse Ke into R is written as Kg, and which is called the global stiffness matrix. Okay, so you can write Kg into D as P. So this is the expression of the entire structure. So the global stiffness matrix K multiplied by the structure displacements D, you will get what? The total force in the structure, capital P. So this is a stiffness equation in structure code as a, when you consider the structure as a whole. Kg into D is equal to P. So you will get Kg as this thing, R inverse Ke into R, or simply R inverse is same as R transpose. So Kg you can write as R transpose Ke into R. Okay, so we have obtained the global stiffness matrix from the element stiffness matrix using a rotation transformation matrix R. Okay, now what is R? R is will reach the equation for R. So for if you consider R matrix, if you consider truss element with 2 degrees of freedom at each element, each node, and A, E, and L are the axial rigidity and length of the member. And then stiffness matrix in local coordinates, Ke you know, Ke is 1 0 minus 1 0 0 0. So we have derived for a element like this. And if you consider the element in the inclined direction, so 1 2 3 4, this one, if I rotate this element by some angle, so these are the local coordinates. So along the axis and perpendicular to axis, and along the axis and perpendicular, these are the local coordinates. Okay, and the global coordinates will be always in global x direction and global y direction. So this is the difference between these two. And the transformation matrix R will be, so for node 1, you can the cos theta sin theta minus sin theta cos theta, and for node 2 also you have cos theta sin theta minus sin theta cos theta. So all other elements will be 0. Okay, so this is a transformation matrix. So this transformation matrix R is for a point P alone. If we consider a point P, now we have a truss element with 2 nodes at each end. So this is the transformation matrix R. Now what is our expression for Kg? Kg is equal to R transpose Ke into R. Kg is R transpose Ke into R. Okay, so we'll find the expression for Kg as R transpose Ke into R. So you have to multiply first Ke into R. So this is, first we'll do Ke, you know, the element stiffness matrix for a 2-noded element. 2-noded element with 2 degree of freedom at each end. You will get the Ke matrix as this, and R matrix is this one, Cs minus Sc 0 0 0 0, and like this. Cos theta sin theta minus sin theta cos theta, and we can copy it like this, and you can multiply and obtain the matrix like this. So this is Ke into R matrix, Ae into Ae by L into Cs minus C minus S 0 0 0 0 minus C minus S Cs 0 0 0 0. Whenever you multiply this matrix, these two matrix, this is 4 by 4 and this is another 4 by 4 matrix. Whenever you multiply this, you will get a 4 by 4 matrix. Now you have to pre-multiply it with R transpose to get Kg. Kg is R transpose Ke into R. So R transpose, you have to take the transpose of R matrix, rotation matrix, and multiply with Ke into R obtained in the previous step. Okay, so you will get R transpose Ke into R as Ae by L into cos square theta sin theta minus cos square theta minus sin theta cos theta, like that. And these 4 terms are repeated. Cos square theta sin theta minus. So this is same as this. These 4 elements are same. You can easily by heart this. And these all off diagonal elements, these 4 terms are negative of these terms. So minus cos square, minus cos theta sin theta, minus cos theta sin theta, and minus sin square theta. Okay, so you have to by heart, this is the Kg matrix. Okay, this is the Kg matrix. Okay, and now we have obtained the global stiffness matrix of the element from the local. So whenever what are the things you require? You require Ae and L of the member and theta, cos square theta, only theta required. What is the theta? Theta is the angle that the local axis, local x-axis of the element makes with the global axis. Whenever you get these 3 terms, you can find Kg of each element. Okay, global stiffness matrix of each element can be found. And whenever we get Kg, use the equation Kg into D as P. So for the entire structures, the procedure is almost same as continuous beams itself. But in order up to getting Kg, it's different. Up to getting the structure stiffness matrix, it's different. Okay, and after getting Kg in the previous problem also, you will solve Kg into D is equal to P. So there were only one K into D as P. We'll be solving for D, and whenever we get D in step number 6 in the previous problem, we'll be finding M as K element stiffness FEM plus PF plus KE into D of the corresponding members. Like that, we have found the member forces. Here also the axial forces in the members can be found as Ke into U as P. So the element stiffness matrix of each element multiplied with U. The element displacements, you will get the element forces. So what is U? you don't know what is the element displacement. You know only the structure displacement, D. Okay, so you can substitute as R into D. And KE into R we have found in the previous step. And I have been substituting that matrix here, KE into R, and into D1, D2, D3, D4 is equal to P1, P2, P3, P4. I have named 1, 2, 3, 4. So from this you will get P2 and P4 as 0. There will be no forces in the perpendicular of direction of the truss element. So this direction and this direction there will be no forces. Okay, and P1 and P3 will exist. And when I write P1 expression, D1 into P1 will be equal to D1 into cos theta plus D2 into sin theta minus D3 into cos theta minus D4 into sin theta. And you can write D1 minus D3 into cos theta plus D2 minus D4 into sin theta. And similarly, when I write equation for P3, you will get minus of this, or P3 will be equal to minus of P1. Okay, and for any element, this is a general so in order to find the element stiffness matrix P1, AE by L into D1 minus D3 into cos theta plus D2 minus D4 into sin theta. So whenever you get 1, 2, 3 and 4 are the coordinates. So along the direction D1 and along this direction D3, along this direction D2, and there may you will get D1, D2, D3, D4 value whenever you solve kg into D is equal to kg into D is equal to P, that expression. From that, whenever you get the values of some D may be 0. Okay, so some of this will be arrested. There will be some supports and some will be arrested. So some values of D will be 0. Okay, and the remaining values you have to substitute and find the values of element forces. The axial force in the element can be found. Okay, in this section we have discussed the direct stiffness method application to plain truss. Okay, so first we have derived the KE, that is the element stiffness matrix for a truss element. So this is the element stiffness for a truss element with 2 degrees of freedom. That is AE by L into 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. And this is the element stiffness matrix for a truss element. Similar to that we have studied for a beam element in the previous problem. Okay, and when we consider the case of a truss, there is axis of each element is in different direction. So it will be, so we have to make sure that everything is converted into a single coordinate system, single direction, global direction. Okay, and for that we require rotation of axis. So we'll be finding the KE matrix of each element in a local coordinate system and we'll be converting it into global coordinate system. So this equation is not always applied when we have found some final expression for the KG matrix. So this is KG, we have found R transpose KE into R, and we have found this is the R matrix, and we have found the KG matrix expression as like this, and you have to by heart this. KG as AE by L into cos square theta sin theta minus cos square theta minus sin theta cos theta, like that. This is the 4 by 4 matrix you have to by heart. So whenever you get the problem, there is no need to do always the local coordinate KE matrix and after that multiply it with convert it in every step. That is not required. You have to directly write the expression for KG of the element. Okay, so C square, like that, cos square theta sin theta, and you require only theta, and theta is the angle between the local x-axis and global x-axis of the particular element. Okay, and you can, after that, after finding kg, you can use the equation kg into d as p and solve the d, that is the structure displacement unknowns. So unknowns of the structure will be finding out. The degree of freedom of the structure will be finding out. Say it may be D2, D4 or D3, D4, like that. Okay, so we'll be finding that one. And after that, you have to find the axial forces in the member. So for that, you can use the expression P as AE by L into D1 minus D3 into cos theta plus D2 minus D4 into sin theta. I think this will be clear when we do a problem. Okay.